Okay, howdy folks. Welcome to NESnet, episode 15-ish, I guess. I haven't streamed in like 6 months, something like that, since March. Just COVID and whatnot, making things a challenge overall, but getting back on this horse. I don't have a lot of formal plans today. I just want to get some of the cobwebs out and start making progress again. I have a new board that I'll explain briefly, and if you're watching this on YouTube after the fact, there's links in the description to the recap at the end. So this is the board that we last worked with. It's one of my MC3 boards with the lattice Mach XO 256, and then we had the ESP01 on a little pigtail because it was soldered on there after we modified the board to get the ESP on there. This new board, I've got it pulled up here, the layout. It's pretty much the same thing. I don't want to do that. I guess I kind of wanted to. Anyway, so it's pretty much the same board, and I've got the JTAG programmer in the top here, but the layout is set up to be able to. There's another one here. Solder an ESP01 directly to the top, so we can actually. We got a board that is in production, manufactured production enough to ship with the ESP. Aside from the little socket change on the board, the big thing is it has a new FPGA. We had the lattice Mach XO 256 before, and now we've got a Gowin GW1N. So it's got like over 1,000 LUTs compared to 256 on the lattice board. The lattice CPLD is entering end of life, and that was the main reason I had to up. So this is some of the stuff I've been working on since kind of stopped streaming. So I have this new board to replace the old one, and it's got all kinds of more horsepower because of that upgrade on the FPGA. The ESP connectors up here, and this has kind of always been on the board, but there's a SD card socket, micro SD card socket on the bottom, and we've got so we do an Action 53 release every few years. I'm a few years late on this one, but this was last cartridge that we released. This is volume 3. Volume 4, the ROM's basically done. The boards are now done. I had to get this all sorted out, and now I just got to finalize and get the release out. But I decided to pair the kind of a sneak release on the Wi-Fi hardware to get it out in the wild. The cartridge is a game release, but I'm putting some of the Wi-Fi hardware on there. Contributors, I'm going to send it to all of them, and then optionally for a few dollars more if people want to add the hardware, and they kind of turn it into a dev cart. So there's actually a second program on the board. The ROM is stored on a 3-volt flash for the game, And then there's a 512 flash that's kind of like the development program. So you can see those in the layout here. Here's the 3-volt TSOP, and then there's a 5-volt PLCC down here. So the first thing that I really need is, and this is kind of what I'm hoping to work on today, is we need a bootloader of sorts between these two ROMs. So my plan is by default the game will boot. This is first and foremost a game release. So that ROM is stored on here, and that will boot by default. Under a special condition, the cartridge will boot from, or the NES will boot from the 5-volt program down here. Initially, my thought was I could put a bootloader of sorts in the game ROM, but that would include me like modifying the ROM, and while that's an option, it's kind of annoying in that I'd rather just be completely removed from that ROM, which kind of helps if this like happens again or something, then we don't have to worry about it. So one of the big benefits that the Gowin FPGA has is, so let's get some data sheets up. It has 9K bit of, where's my, nine K byte, yeah, of RAM, block RAM inside the FPGA, and we didn't have anything like that. This one, yeah, go in, yeah. So there's user flash. I think there's the family table down here. This is our device. So there's a 1152 LUT4s, 800 some flip-flops. There's no shadow RAM, but there's 72K bit of block RAM. Those are in 4 different arrays, and then there's 96K bit of user flash, so it's like 12K byte. But I think this is, in a way, it's more, you know, kind of get to my plan here. So there's, yeah, we don't have any multiplier. We do have a PLL, and yeah, those are the main things. IO and stuff, it's pretty similar. So I've already tinkered around a little bit in a different design, getting the block RAM to run as program for the 6502. So instead of having an actual program SRAM on here, we can put the RAM inside the Gowin. That SRAM, we were able to actually define what the startup state of that RAM is. without even using the user flash, from what I understand. So we can define the startup state of the block RAM, and which means that we could put code in there. If we can put code in there, then we can effectively have the 6502, the mapper, power up, where it's basically like an 8K byte ROM only mapper. I don't really need any CHR. The CHR RAM's there if you wanted it, but I just need enough code space to check the controller at power on and define some sort of sequence, like hitting select an A or down select A. I don't know, something that's unlikely to happen. If it does happen, it's not the end of the world, but if those buttons are held at power up on controller 1, let's say, then we can power up, we can enable, so the boot ROM will have to write some make some writes to the mapper to get the mapper to enable our development program, and then it can jump to that reset vector that's present there. If nothing's pressed, right, you just power up the console normally, then make some mapper writes to enable this ROM and jump to the reset vector, so it'll just play Action 53. Is kind of my plan. So I already have 2 ROMs flashed on this board. It's volume 3 I have flashed on the 2 megabyte, and then I have part 1 of a smaller version of that ROM on the 512. So it is working. So right now, okay, so this is a smaller version. There's only 2 tabs here. My current Gowin project. Where's the, here we go. Well, I think I'm gonna make a new project. I kind of want to leave this one. It doesn't know where that file is. Accidentally deleted or something. What happened? I'm gonna turn my own music on, but I'll leave it muted. Pick your own. Let's see. It's right here. Oh. It's looking for Action 53. Wait a second. Oh, I think I messed around with this after the fact. There we go. I found it. So this should be what's flashed on there currently. And I just have a little section here. These lines will boot off of the PLCC flash, the 5 volt, and then these lines will boot off of the 3 volt flash. There's a small difference in here because there's a level shifter for the 3 volt flash. So we have the data coming out of the 3 volt flash has to go through the level shifter, or the 5 volt is just connected straight to the bus. So there's some extra logic in there, but so let's just create a new project and not break my working one. So I already made the folder. Although I think I need to it doesn't like that. I said force it. There we go. 1N. So I'm using Gowin's FPGA designer for this. You have to have a license to use this. It doesn't cost anything, but it is a bit of a challenge if somebody else wanted to release or to work on their own FPGA build for this. I don't know if anybody really want to do that, but there are some open source options. I'm not 100% sure if this device is supported, but I know there's some open source tool chains in the works. So might tinker around with that later, but not any for now. I'm just sticking with what works. So let's grab this file, my constraint file for the pinout, and the original source. Drop these in here and add these files to the project. All right. Place and route. And then we can flash it. So the flashing process is a bit, oh, I forgot about this. We always have to do this. Dual purpose pin. So I dual purpose all of these. These are specific purposed pins on the FPGA. So JTAG is normal JTAG, TCK, TMS, TDI, TDO. You can use these as general purpose IO, but you have to toggle those between actually working as JTAG or general purpose IO. You have to toggle this JTAG enable. So you have to pull it low, pull up. Yeah, so I think you gotta pull this down, force it low to use these as IO. I have them connected to my kick, so we can do different things there. But just some of the other ones here. So reconfigure, taking this pin low will cause the FPGA to reconfigure from whatever's currently selected. I don't really need that. Done tells you the JTAG, it's done with its reconfiguration. Ready, I don't remember. It can, mode is a big one. The mode pin, it has to be low for the FPGA to configure itself from internal flash, which is normally what we want. But it has to be low at power up. And if it's not, then the FPGA will try to configure itself from an external SPI flash using these pins. And I don't want to do that. I just want to use internal flash anyway. So there's kind of some trickery that goes on here. I wanted to be able to use this mode pin for something else. I don't really care. I just want the thing to boot and work. And every IO that's there, I want to use it for something useful, not just configuration. So I getting familiar with this device, I had to go through all that. And my solution is the kick lockout chip controls this MC, or it can. And I didn't want to require a pull down resistor or a jumper or anything like that. So, and the kick doesn't boot up fast enough for the FPGA when it first powers up, power and reset. This pin ends up being high and it tries to boot from external flash. It fails. When the kick finally powers up, I mean, it doesn't take long, but it takes longer than the FPGA. It takes this pin low, and then it could toggle reconfigure on the FPGA to get it to reconfigure based on, now we have mode low. But I want to use this pin for something else. It's just a CHR ROM or RAM address pin. I didn't want to have to use it for that. This pin is output only, which is annoying. So that's why I didn't use it as an microcontroller pin. But I send the reconfigure command over JTAG from the kick. So the kick lockout chips over here, it has some connections to the JTAG pins on the FPGA, also the ESP. Anyway, we check all of these. And the other gotcha, it took me a while to figure out, is you gotta select 24. Well, you need something faster. This clock right here that we're selecting is how fast it pumps the configuration data from the internal flash to the SRAM fabric of the FPGA that controls, the logic that's behaving as. We need that to be relatively fast because after a few milliseconds, it's like 15 milliseconds or so, the 6502 is going to come out of power on reset, and that's going to be looking for the reset vector. If the FPGA is not operating as a mapper and making that last bank of ROM available, the 6502 is going to power up and crash. Why the default's crazy slow, I don't know. The data sheet, I think, has like recommended fastest is 24. You can do these other ones. I've tested them. I think like maybe 30 works or 40. But like these 60 and 120 megahertz is too fast. It fails to copy over. And this is plenty fast anyway. And then I select binary bitstream format. It actually creates both when you do this. But my programming setup, I use the binary with INL Retro. So apply all those, and now it actually reconfigures. Or not reconfigures, but synthesizes our data stream. So we can test flashing this quick. This is kind of my general purpose, or not general purpose, but I don't know how to say it, but so this is just a Lattice dev board. It has a I forget which chip, an FTDI chip that translates from USB that the application's talking to JTAG. So it's a USB to JTAG chip, I guess. So this is an external programmer. I have things set up to where the lockout chip can actually reconfigure the FPGA, and that'll be the end user option, so that you can use the INL Retro to reconfigure this FPGA to add firmware. The device is going to ship where all of this extra hardware is disabled. So to unlock that hardware and do something with it, you're going to have to upload new firmware, and this way I don't have to have everything done when we release the game and the hardware. Eventually that won't even be necessary, because once things are mature enough, the lockout chip will be able to get new configuration data for the FPGA from the ESP or from the SD card. So the cartridge will be effectively a standalone device that doesn't need external tools. The INL Retro program in the FPGA works, but I have some more work to do specifically around this block RAM stuff. Currently I can reconfigure it, but I can't set the starting value of the block RAM. I need to add support for that. So that's why I'm using my external programmer right now. But let's so let's select the one that we're actually building from. So this FS file, it created both of them. Embedded flash, erase program, verify. Yeah, this is all looks proper. Quit ID code mismatch. Oh, I think the problem is I might have. Let's try this. Yeah, so one kind of annoyance, because I have two ways of programming it. Right now I'm just connecting to the ESP header, which is also connected to JTAG. But the lockout chip also controls JTAG, so they can't both be running at the same time. So my hack solution is just have a switch on the back of the board to hold reset low, so that it can be configured externally. What really needs to happen is the microcontroller, the kick microcontroller needs to let go of the JTAG bus, but it's probably going to be doing other things when those are dual purpose for other things that we're going to be making use of here. So yeah, it looks like it successfully programmed. It didn't reconfigure itself because of all of this situation we were talking about earlier, but that's fine. So now we have to have the kick working. Flip that switch back. And and we should boot. Okay, so we've got a good starting point. All right, so this is our current Action 53 mapper configuration. You can see we're using the PLCC flash. Here's for the TSOP 3-volt flash. So our PLCC here and TSOP here. So that's, we've got part 1 ROM, which is on the PLCC flash. So everything's working. As a starting point, we don't have any block RAM running right now, so let's turn my alarms off here. Let's add the block RAM to our implementation. So our goal is to get the block RAM working as a boot ROM, basically. So where did I can kind of I think there's a user guide for block RAM. Hey, Sakanako. Yes. Yes, doing our Wi-Fi stuff for the Action 53. So this is going to be, I'm putting the hardware in there for all the contributors so they can tinker around if they want to. And then if people just buying the cartridge want it, then I'm going to have it available for like $5 option. So hopefully, it's really just a cheap way to get hardware out in the wild, and as things mature, hopefully there'll be some people that have the hardware and can help test to combat bugs early as far as the networking stuff goes. So we want to have a boot ROM that selects between the 3-volt flash for the game and the 5-volt flash for the development ROM. I'm going to put a little boot ROM in the block RAM that's inside the FPGA. So there's actually a configuration tool. What is it called? IP core generator to block memory. So this memory can be dual ported, which we'll ultimately want. This RAM, right? Block RAM. We'll end up having it available to the 6502 as program effectively. But the real power of this is that the ESP module hanging off the board here on the microcontroller, this guy is going to be able to read and modify the program at the same time that the 6502 is accessing it. So we wouldn't necessarily need true dual port to do that. We could just do time sharing, most likely, because 6502 is so slow, but we got true dual port, may as well. We don't need it as true dual port. For our little boot ROM. Where are we at here? We only really need it as single SDP semi-dual port, which anyway, single port block RAM. This is all we really need. So you have a couple options here. The way this stuff is configured is there's four separate block RAMs. They have it here as one chunk of the FPGA, but it's split into four. It can be configured a number of ways, but the way that we really want it is so 8 kbytes, 8 times 100 a kbyte 1024. So that's an address depth of 8192. Data width, we'll do 8. We could actually do 9, which is, if you had like ECC, you'd want that 9th parity bit. It's kind of useless for us. We maybe, as far as the 6502 side is concerned, maybe that 9th bit could be useful to where it's visible from the ESP side. So like anytime the 6502 writes to a byte, we could use that 9th bit as like a flag of, oh hey, this bit or this byte was written to. And then the ESP would be able to sense that, to know that something is updated, and they would acknowledge update, and it could clear that bit. So it could be useful in that situation, but for the boot ROM, that's all I really need it as. So this, let's see, we hit calculate, so it uses all 4 blocks. It doesn't need any flip-flops or muxes to do all of this, and you can provide a memory initialization file. So this is one thing that we're gonna need, and I don't know how to do. What I have to figure out. What sort of file? I don't know. So this is an FI flash initialization file. I wonder if a bunch of words that aren't actually MI. .mi doesn't come with anything. The documentation on this Chinese FPGA isn't the best, but it's okay. And I've got some, I feel that some FAEs available if I have problems, but I'm guessing this is going to be similar format. So comments, it appears, and then data is this address. So the first number in the array in the RA address with the bit width of 6. 0, 1, 2, 3. And the address range is 0 to 47. The second number, oh, okay, so I think it's saying this is the row address and this is the column address, which is probably not going to be the same. Followed by 8 data, hexadecimal, 32 bits wide. So this feels like a text file. Anyway, let's just create a file. And point it at that. Here's, we can probably put a comment in there. Open. So these, the thing that we'll figure out, I guess, but the configuration of these block RAMs is kind of funky. It has been a while. Wow, Jinxie, like 6 months. Finally getting back on this horse. My Alwa streams are officially done. Which was like kind of partly related to my hiatus. Streaming when COVID first started hitting us was a challenge with the kids homeschooling all day, and then it was summer. Good to see you back again, though. Getting going during summer. I had some health issues I was dealing with, and yeah, I'm ready to get back at it, though. So, as far as my future streaming goals, I want to keep going with this Wi-Fi stuff on Fridays. We don't have any Alwa project anymore. The Elden Pixel guys are took over that. They're doing their own thing, which is fine. So that frees me up. So my goal is yeah, doing okay though. Just difficult, but in a better spot now, ready to go at it. So maybe on Wednesdays we'll pick those back up and start working on an online game to put on these boards. It's kind of my hope. I don't know what. I haven't fully made up my mind. Part of me just says do a chess game, because there's already don't have any sort of licensing concerns over a chess game. I don't have to come up with the game. The game already exists. The other thing is you don't need an NES to play chess, right? We could have it on the NES, but there's already servers of people playing chess, so you could just get on there and play with anybody, or you could. I've played chess with one of my old Navy buddies on here. You can create a private game and play, and they have like extensions. Oh, you got the alerts on. Good stuff. Yeah, haven't seen one of those for me for 6 months. But yeah, so this live chess has extensions to where you could have a physical board, and play somebody remotely with a physical board. Well, our physical board could just be the NES. So that's kind of like one of the appealing features of doing chess. It's a little bit boring in that it's chess, and I don't think there's gonna be much interest in that, but it's also a good demo. Just like Pong's a good demo. Effectively, yes, it's on mobile and stuff too. So live chess is already, I assume that's how you pronounce it, is already an existing server, and all these. I mean, you can watch. We're watching somebody play right here. It's got 67,000 players on there right now. Now most of these people are playing probably on their phone or in the browser, but there's an API. So there's already an API and everything built up for it. I think it's the main point is, or one of the reasons for it is to be able to play on a physical board, and the NES would just be our physical board. We just have to communicate with these servers and say this piece moves to this place, and so we wouldn't have to do all of the server stuff to be able to play. They already kind of took care of it for us. So that's kind of, because that ecosystem already, and this API already exists. It's appealing as a project. So maybe we'll do that. But we gotta get this board going first. So when we're at the point I started thinking about a game, maybe I'll pick up the Wednesday streams. Yeah, and that's kind of my thought too, is just the universality of it is like, I don't really have to think about the game development, and it takes care of a lot of things for us, and it's good, it's a good demo. People, I could open source all of this, and then people could use it to do it, and then we could have a version where we make our own server and find people that are on their NES playing, and chess is chess. So the header information in the initialization file is missing or illegal. Please check it. Yeah, well, we don't know what to put in there. Let's just search .mi. Yeah, I don't think. Tetris 99 is an idea that crossed my mind as well, and now Mario 35. So those types of games are pretty friendly to online play just because latency isn't important. When you score Tetrises or kill bad guys on Mario 35, you're just sending bad guys tiles to your opponents. If those don't arrive immediately, you know, they could arrive 5 seconds late, and it doesn't really matter. But the challenge with like doing Tetris 99 is there's copyright concerns. You know, if I don't have Tetris Company's permission to do it, you know, then am I never able to share it with the world because I don't have, yeah. So that's one of the appealing things about chess is that's not a concern. But you know, we could, one of my other ideas was kind of do a Tetris 99 Mario 35 type thing, but then we have to come up with a game that's original, and maybe we wouldn't have to get too crazy, you know, to come up with some block or matching, or you know, those are some I got some similar ideas kicking around in my head. I don't know. If we're going to find documentation that tells us what this memory initialization file is supposed to look like. Shadow SRAM, which is a separate SRAM, can be initialized, yeah, from the software, but you're not going to tell me how. I wonder, it tells us how to do the flash. Let's just, well, what if the file exists, but it doesn't have everything in there? Will it like generate something for us? So it's telling me, oh, that error exists. Yeah. Yeah, no content in the memory initialization file. Let's see what Google can tell us, maybe. I think this is probably just a data sheet we're already looking at. The memory initialization file can be written or generated by the menus. Oh, let's try that. Let's get rid of this. Just cancel that. So file, new, memory initialization file. Okay. We can manually type in our ones and zeros. View hex base value address base. Oh, okay. We got 8-bit words. It's just always going to do it this wide, I guess. So let's do this. Go to the last byte. So put FF at the end. 1, 2, 3, 4, 5, 6, 7, 8. And save. Let's open up a new window. All right, so our action 53, it should have go when generated. Edit with Vim. Hey, there we go. So that's what our file needs to look like. Okay. So if we get this working, we can hand type in our assembly code. Probably, well, a better way, right? So we can build a 6502 boot ROM with CA65. Export it to a binary, NES file for the program. But the Gowin, to get that code into the block RAM at the program is what we're making it at boot, it needs to go through this file. So we could create a Lua script or something that converts from a binary NES file to a from a binary NES file to this memory initialization file. But we at least have a way of doing it now, probably. So let's close this. Let's make our Let's delete that one. So it should be valid now. 192.8. All right, so it's going to overwrite that file. Yes. Yes. Okay. So this is interesting. So, so this is some of the code it generates for us. This is the block memory module. We've got 8 bits of data output. We've got an input clock. This is synchronous RAM. We've got an output enable pin, a chip or clock enable pin, chip enable, same difference, I guess. We've got a reset. We've got a write enable, and then we've got 13 address pins or signals for input, and we've got 8 data input. And then so when we were doing the IP generator, right, if we do 8192.8, so before I entered those values, right, it only needed 1 block RAM to do the 2 address bits, right? 2 address bits, or the address depth is how many words, and the width is how wide is the word, right? So here it's saying there's only 1 data pin, a data in, a data out, and then you only have 1 address pin. It's either high or low. So this is just a 2-bit memory. It only needs 1 of the block RAMs to implement this. There's 4 available, but there's 4 available. They have 2 point something K byte total. Anyway, so if we do it this way, we're not completely maximizing it because we could do it 9-bit, but we do 8 K byte, 8-bit word, right? It's going to use all 4, and it doesn't need any extra resources. The problem is you've got these 4 separate block RAMs. If you did them how you might think normally, where each of them is 8 bits wide, and you have 4 separate ones, now you need multiplexers on the output to select which one you're reading from. So that's going to end up using flip-flops and muxes in the logic fabric to implement that type of memory. What this does is the 4 separate instances of block RAM, it uses them as 2 bits wide. So here instance 0 only has 2 data bits. It still has 13 address bits, but it only has 2 for data. Each one of them is a 2-bit wide, right? But here instance 1 is used for bits 2 and 3. Instance 2 is bits 4 and 5. So really, the memories are the other way. It's kind of like how the Commodore 64, the early models at least, I think, they're 64K bit RAMs, but each RAM is only responsible for 1 bit of the data. here we have 4 block RAMs, and they're each responsible for 2 bits. But you don't need any multiplexing or anything because you always get bits 1 and 0 from the first one and 766 from the last one. So this is like ideal. If we do 9-bit bus, this is using all of the block RAM because there's an extra bit available for parity. And we calculate, now all of a sudden it can't do that anymore because 9 is not an even number. It ends up having to, I've kind of looked at what it generates. I think this does it. So each block RAM can be arranged for 9 bits wide, or 18 bits. The data sheet user guide goes into some different options. Semi-dual port. Single port. So you can do it 2 by 9, 2 by 18, 512 by 36. Right, and here's your data. So when we do 8-bit bus, it actually does it like this, but it does 4 of them to give us an 8-bit data depth. But when we want that 9th bit, it has to do it like this, and needs a multiplexer to select which one. Anyway, so the memory initialization actually happens on it takes it from our initialization file and then brings it into this source file. So that's kind of annoying because we'll have to go through this process every time to have it regenerate this source file, but I guess it's not that big of a deal. It's interesting. So these are actually like initialized in 256-bit widths. Our data doesn't really look like it originally did. 3939 059 because we had 0 through. This is our initialization. What am I looking at? Nothing. Anyway, I'm not going to try to figure this out, but it seems to be working. So we need to in our source code import this module so that we have a block RAM with initialization. I've kind of done this before, but just updating this MI file alone is not going to be enough. Anytime we change our code, so it just opens it here. File open. Is there a way to get that? Oh, if you just do open normally, it'll do this format for us if we don't want to do it manually. Anyway. So we've got a Gowin single port .v. I want to do that. Let's close this and I'm just putting it in here. Yeah. So this is the file that's included in our project, but we need to instantiate this module. And I think this temp basically tells us how to do it. So this is an old project that I tinkered around with just to test this block RAM working. It wasn't initialized or anything. I copied the code over, but we're not really going to want to do that because the initialization data is in there, and we want to be able to generate that each time. So we're going to put this at the in here, the end of our file. So it's within our mod. It's within our main module. I always forget how to do this stuff, but yeah. So this is my other MC3, right? So this is the final end module, and you can define other modules out here, but this is kind of like what we have, except it's in a different file. So we need something like this. So Gowin SP, which is what it's actually called, and we can just call it VRAM, whatever we want to. So the why did I give these different? Oh, I think I renamed things. These are the signals that we actually need, though. Oh. Wait a second though. So here's part of the this block RAM is not tri-state. The data, there's two separate data buses. An input. I have a picture for us. Yeah. So it has data in and data out. That's just physically how the RAM is constructed, which is normal for a FPGA. We will need to create a so the circuit board itself so this is data 5. Here's so we got a level shifter with the CPU bus. So this is literally CPU data bit 0, data pin 0, coming from the cartridge connector. We got 0, 1, 2, 3. These all flow up the circuit board to our level shifter. 0, 1, 2, 3. Anyway, they go through our level shifter. So from 5 volts down to 3 volts. And on the 3 volt side, they connect to our 3 volt memory and to one of the pins of the microcontroller. This is a unit or a bidirectional data bus, right? So we need this the CPU to be able to write to the mapper, but then we also need the CPU to be able to read from the mapper. Normally, you wouldn't. Most mappers like MC3 and stuff, you don't have that. You're just writing to the mapper. You're reading from the memories. Well, here we have a memory inside the mapper. And it's physically constructed like this. So we have to converge the input and the output into a same signal, or at least to the same pin. So this is how I did it on when I was tinkering around with MC3. So I created another module on top, an in-between module in between the Gowin single port block memory that they instantiated for me, or created, whatever. I don't know if instantiation is the right word, but whatever. And here are the standard signals: data out, data in, right? A clock. I gave these new signals. The output enable, I just always enable the output. I always enabled the clock. I inverted them, because up here I think of them as active low when really they operate as active high. Don't need resets, just always low. So these data in and outs I have going to a buffer, and this buffer has an output enable, an input, and an output. So the output of this buffer is just the data pins. We gotta set these to in out because they're bidirectional. And then we have a block RAM. The output from the block RAM goes into the buffer. So this allows us to we creates a signal to we can control when the block RAM data is being driven onto the pins. We only want to do that at a specific time. So let's see here. So I already have my buffer down here. Okay. So we need this module. But how many? Yeah, so this is actually Verilog here. We haven't got into, although we kind of are. Our end goal is to put KOTD. Go with that. Yeah. We've got RAM inside our FPGA, and we can put code in there in that RAM, and we're going to make that the first memory that the 6502 boots from. So right now inside the FPGA we are writing Verilog to oh, you're getting hit by a hurricane right now. Yep, this is the Verilog for the FPGA, and this is where we're actually going to put our assembly code, which isn't super convenient. We can come up with better ways of doing it, but this is how the tool is set up to be able to provide initial values for this block RAM when the FPGA powers up. And so we're going to put our little bootloader code to select between two different memories, so that, not bad, yeah, hit your power lines and internet connectivity. So this ROM is going to control which memory is enabled, and their game's going to be stored on here. But then to develop, if you want to develop a Wi-Fi game, this memory will be available. So what's your question? KOTD. All right. So I'm just kind of copy pasting things from this other project where I had block RAM working as program. The 65816 naturally has a 6502 mode. It powers up in 6502 mode, and I think in that mode the first 64 KB of the 65816, yeah, so the first 64 KB are the 6502. You might be able to change it to where the different banks, the 6502 can execute off the different banks by changing the, I don't know, I've never really tinkered with it, but most SNES games just start up, get out of 6502 mode into 16-bit and operate from that way. But yeah, so you can't, there's while the Super Nintendo contains the 65A16, which is a 6502, you could execute binary, assembly code. You could execute NES code on the Super Nintendo CPU because they have a compatible processor. But yeah, the audio, the graphics side of the Super Nintendo is completely different than the NES. So, if you had some game logic, right, that's just dealing with memory of the 6502, that stuff will easily port over. But you may have some code that interfaces directly with PPU. You've got to have some in your game to display anything on the screen. That's not going to be. Yeah, I guess. You could put a PPU in the cartridge, but then the video is going to be generated on the cartridge. So, because you could map anything on the cartridge if you wanted to. The whole address space is visible, but you're only going to be able to map things on the cartridge to the cartridge. Yeah, right. You to the Super Nintendo PPU, and it's completely different PPU. Behaves completely differently, completely different memory architecture and everything. So like Super Mario Brothers All-Stars, right? They released these games, Mario 1, 2, and 3, on the Super Nintendo in a multi-cartridge. Or is it Mario 1, 2, and 3? It's Super Mario Brothers, Lost Levels, Super Mario Brothers 2, and Super Mario Brothers 3. It's possible that some of the original assembly for the game engine is ported over, but all of the graphics had to be changed. All of the interactions with the PPU, all that code they would have had to rewrite. But there's disassemblies of the NES version of these games. It'd be interesting to see how much, is the jump code, how many pixels Mario moves when you jump and stuff, is that identical, or did they massage it? I don't know. Later version included Mario World. I didn't know about that. Really? 25th anniversary edition. Is it that? I didn't know about that. Interesting to see if you can make FPGA or small hard make. Yeah, and it's like the memory map is kind of like the least of your problems. The majority of your problems is just in the audio and the graphics, which the cartridge can't really do anything about. Although I guess maybe you could put some, the only thing that I can really think of is what if you had if you emulated the PPU on the cartridge, right? The NES PPU on the cartridge. So the Super Nintendo CPU in 6502 mode could make these writes to its memory map, its native NES memory map on the NES, but then the cartridge would have to translate. So it would have its own PPU, and then maybe you could, writing a very generic one would be tough. but you might be able to do some game specific ones. I mean, they got NES on a Mega Drive now. It's like kind of funny, but I think there's a PPU, an NES PPU. Where is that? I don't remember I saw it, but Crits just did it with the recent Mega Drive. So maybe the PPU that's on the cartridge could then the output of that PPU would be, code or binary data that would then get copied into the 68K in this case is spending time. I think in this case there's 6502 and everything, right? Is emulate the CPU and the PPU emulate on the cartridge. They're running on the cartridge, and all the 68K is doing is taking the output of the digital PPU and throwing that information into the VDP, I think that's what it's called, the Genesis GPU, effectively, and for audio, I guess. Well, you can actually port audio straight into the cartridge. Yeah. Oh, I don't have any use for it. It's just a curiosity of mine. Not that I'm really willing to do anything more than mention it. that's yeah, it's the translation of an NES PPU into the PPU of whatever console you're in. It's tough. You can actually cheat with the audio because Super Nintendo, I think, and the Genesis, you can have audio. Yeah, that's what the Super Game Boy does for Super Nintendo. It's just the audio comes straight out of the Super Game Boy to the pin, and then that's just ported straight out to the console's output. But you also have like systems that aren't even really that. There's like a Game Boy Advance. Retrobit makes one, but really all that's happening is the Game Genie style device cartridge plugs into the Super Nintendo, and you can put a Game Boy Advance game in there. It's all being emulated on the cartridge, or just hardware replicated, whatever. It's just getting controller data from the Super Nintendo controller, but the video output and everything is on the cartridge. It does nothing. The Super Nintendo PPU is doing nothing. Anyway, so let's get back out of here. We need to connect up this block RAM. Yeah, yes, sorta, with some crazy trickery. I would have never thought that like having an NES emulator on a Sega Genesis, but yeah, they're doing it. It's not like amazing. Like, it's more of not like the why do it is like for fun, not because it's the best way to play NES games, but it's just technically cute. So we're gonna need this buffer. Did I already copy this over? It's just I think it's amazing, but yeah, you gotta have fun doing that stuff. I mean, people would say the same thing about what we're doing here. Why are you connecting the NES to the internet? Why are you putting Wi-Fi inside a cartridge? Well, because we can. because people are excited about it. Oh, they want it. Let's do it. Yeah, they use the same controller read register, but the controllers, I think it would still, the buttons don't exactly. I think you can wire up a Super Nintendo controller to an NES and play games, but I think it's like instead of being B and A, maybe it's or you might want it to be Y and B, but it's being, I don't know. There's something that's like a little bit wonky if I recall correctly. Oh yeah, you do? Well, he probably, I mean, you could probably make one yourself if you wanted. I bet if you reach out, I'm friends with Andrew. I'm sure he would share the files and then if you really want to make one. I don't know about all the part of it's like the board is like in some ways the easy part. It's like all the other code that he has running on the microcontroller that's then doing something interesting with it, which is, but you never, I mean, reach out to him and he might have them sitting around, just give you one. I don't know. I've never asked him. I don't really have a use for it. It's cool though. Yeah, hit him up. I mean, you send me a whisper or something. We can, so I can hit you up outside of the stream and see if he has something. So we have our bidirectional buffer, 8 bits. We have an output enable, an input and an output, and it's just it's simple. If output enable is low, the output port equals the input port. If it's high, then it's just tri-state. So the connections for that, we have a block RAM signal that we're going to generate from our memory mapping. The block RAM data output and data is, so this is literally just cartridge data. So we need to generate this signal, block RAM data out. I think we're basically going to do the same thing we did here. So this is my Road Blasters board for the arcade. Outputs 15 kilohertz RGB-C signal. What are you doing with it? Oh, so you want to output it to something usable. Yeah, I don't really deal with that video stuff. I wouldn't. Can't give you any insight there. So this, okay, yeah. Never hurts to ask. We want this to be block program. So this is my program block module. Okay. So this is how I think of the block RAM module from my perspective, right? We have an input clock. We have the 6502 clock, right? So we need to know if the 6502 is currently trying to read or write where it is in its cycle, because this memory is not asynchronous. We can't just connect it like we would a normal SRAM. So we have to have some sort of knowledge of the current cycle state of the 6502. We've got a block RAM chip enable signal, right? So when is this memory enabled? We've got an output enable, when are we reading from it, and a write enable, when are we writing to it. We have 12 bits of address, or 13 bits of address input. 13. Shouldn't this be 13? It's 8. It's 8 kbyte. Getting mixed up here. 2 to the 13. Yeah, that's 8 kbyte. Why am I? Oh, A14 would be 16 kbyte, and then A15 is 32. Adapter for cartridge slot to serial on PC. I mean, that's in a way, that's kind of what the INL Retro is, except not serial. Well, universal serial bus USB. So the Retro is kind of like that. The reality of it is you can't make, serial bus, or maybe you could do parallel bus fast enough, but nobody does that anymore. But you really have to dump the cartridge onto the PC. You could, hide it as far as what's actually going on. You don't have to save a copy on the PC. It could just be a volatile file that gets lost. But you can basically do that. That's basically what the INL Retro is. I just don't tie it together with an emulator, force you to dump it to a file, and it's also tricky just from the mapper standpoint. Anyway, so we've got 13 bits of address, and then I keep this using the PC. Oh, the PC as a mapper of sorts to send the ROM data to the console. I think I'm thinking this backwards. Anyway, so you're saying, I mean, we're kind of halfway doing this with our Wi-Fi project. It's not connecting the cartridge connector in its entirety, right? We've got our FPGA, which is fully accessible to the 6502 through the cartridge connector, right? But then we're going to have our Wi-Fi module up here. If I could highlight the connector. Sitting out here. But yeah, it's not I mean, it's a wireless connection. I mean, you could just so the mapper is just going to be using serial to communicate to this. You could instead do it completely wired and use a USB to serial adapter and connect that straight to it. But your bandwidth is limited there, but the 6502 is slow. Anyway, so you could have, game state and other things running on even a server somewhere else. You could do it. And I mean, to some degree, how you define things, if you make the chess game, it's fine. My main goal for this stream today is just to get things moving again. My goal was to start streaming at 9 this morning, and I didn't start until now or 1 o'clock. It's just one thing after another keeping me. I almost didn't do it. But yeah. So this is our block RAM. And then inside this module, wait a second. Oh, I see. Yeah, getting started is usually the hardest. But once we get going and brain thinking about it, it's easy to pick back up again. So I have this entire thing as one module. Okay. And this buffer is a separate module. Okay. So this is going to I've got 3 modules total in my file. Right? So I've got the top module, which is just the entirety of the FPGA. Everything is internal to that. Inside that module, we have to instantiate or call any other external modules that we want to include. So we've got a block program, which we're just calling our boot RAM, and these are the connections we're making to that other module. And then we have a buffer to handle the data, because this block RAM has an input, a data in and a data out. And so this buffer is going to control which direction it's going. Now, the block program module is just the one that I define. It's mostly me renaming and changing these signals to what I'm used to, right? So this is just direct connection. So there's an FPGA clock, which is a synchronous clock. It's just connected to clock of the Gowin module. We've got M2. I don't do anything with that. I thought I was going to need it, but I think we got by without it. Block chip enable. So when it's enabled, when this memory is enabled, we have to enable the clock. So it's just an inversion from active high to active low. Output enable, same thing, and write enable. Address, we just connect it straight up from the CPU bus. and then we have a data in and a data out. So, and no reset. So this is a little primitive, but we can generate these signals elsewhere. So when in our memory decoding, when we say that the WRAM is often what it's called, is enabled, that's just going to go straight to the chip enable. So I'm doing that. Where? Oh, I haven't created that yet. In my MMC3 one, right, I do it here. There's a enable bit in the mapper when the 6502 address bus, A13 and 14 are set, ROM select is high, and the clock effective, which is delayed for the ROM select delay to account for A15. Then we're going to enable the WRAM or it's disabled. So this effectively lets me think about this SRAM as if it's not inside the mapper, which is how I'm used to doing it. Okay. And then we have the buffer module to handle the data separately. This is just connections. All right, so I think this is just going to work if we create controls for these other signals. The Gowin SP, get rid of this, is this module that the software generated for us and includes our initialization data. So that's all the dots connected. I don't 100% know that we have the inclusion proper, but it's included in our Verilog files that go in a single port. So I think it's okay. Okay. So when do we, let's change this to B instead of, so this oscillator is, there's an oscillator included in the FPGA, so I'm just using that as the source clock. What speed do I have it running at? So if the frequency divider is 12, we get a 21 megahertz clock. Here, just some other random notes about for the M2. So we need to generate these signals. Oh, I think, yeah. So we need to instantiate these inside our top module. So when do we want to enable these and all that? So this is the WRAM that's actually on. There isn't one on this board, but if it was present, it would be controlling that. So that's part of why I like using the B for the block. Let's just put we gotta make sure that we're accounting for the external level shifter to this level shifter for the 3 volt to 5 volt or 5 to 3. So if CPU address makes more sense to do it that way, I think. If they're both set, M2 and ROM select are all set, but I want to do M2 effective to deal with the ROM select delay. So we can just change that to such. This basically we need to know if CPU address A15 is low, and the only real way that we have access or indication of CPU A15 is ROM select, but ROM select is only so ROM select is an inversion of the M2 signal when A15 is high. Otherwise, it's just high. So this is when memory is enabled for the cartridge. I don't like this memory map. Yeah, I kind of like this one. So normally program is from 8,000 and above. Why do they put a 10,000 there? It only goes to FFF. But anyway, so when the 6502 is accessing this space, ROM select will go low to enable the program. We're effectively putting the block RAM here right now. So we need to know when that's low. When A15 is low. Anyway, whatever, but so in this case, that's when we're going to say that the block RAM is enabled. So this is my MMC3 code. The MMC3 RAM isn't always readable. Well, let's do it like this. We only really need to enable So if block RAM chip enable is low from up here, then we're going to enable the output enable signal. Really it doesn't matter. That just can always be enabled because it's going straight to the buffer. Well, oh, hold up, that's not true though. Because we're using this to control our buffer as well. So we'll be conflicting with the program. For a read. That looks wrong. Because I'm thinking about this from like a traditional SRAM. You can leave output enable enabled, and if write enable goes low, it won't output. Write enable basically overrides output enable. But that's not the way that we've set this up. If block RAM output enable is enabled, then we're going to drive the data bus with the memory. I'm just going to, this is my MSC3 code, I'm just going to make this note so it won't synthesize next time. It worked. Okay, so we're gonna do this. So if the SRAM is not enabled, it's just those signals are going to be high. If it's low, we say if this is a write, else so in a read, we're going to enable output, we're going to disable write, and for a write cycle, that looks right. Correct. So let's see, we generated the signals that we needed. I think it might synthesize now. Probably got some syntax errors somewhere. Let's synthesize quick here. Let's see what we got. Expecting N module 643. I think we're missing an N module right here. Let's see if that fixes it. Oh, we forgot our... This is now input and output. Bidirectional. That was successful. One thing I'm a little worried about is these guys. Let's just try to place and route. Whenever you change these package inputs and output pins, it likes to throw away my constraint file. But I don't think changing them to bidirectional pins is I think that's okay. I don't think it's going to trash it. So it looks good. In reality, we probably want these to be slow slew rate. We'll do that one more time with those set to slow. Yeah, here the direction is in out on these now. That's good. Okay. So if we flash our board, it should now have program, CPU, extra CPU RAM. We won't have amazing initial indications of that because ID mismatch. Oh yeah. Disable my kick here. I forget to do that. Did I have a problem again? Did I? Okay. Looks like it's good. So We should have at least not broken it. If it's not broken completely, then it'll still play as this game. Oh, I forgot the kick again. I need to update that code so I don't have to do that every time. Okay. So we didn't break anything. Oh, you know what I think we forgot though? That's weird.
Make your selection now.
This, when the so in the PLCC flash, the 5-volt program is enabled. The only reason that data direction needs to change is when we are reading from the internal block RAM. When we have the 3-volt internal memory, then it needs to change if we're reading from the program behind the level shifter or the block RAM. I think we can just leave that. Next, if we're reading from the cart, I'm only going to enable the level shifter output when M2 is high. So the way that I was thinking to test this is just use the INL retro to read. We could flash a different test ROM. they would actually test it for us. Maybe that's easier. It might be. Let's go for easy. And if that's working, then I think we're just going to call it. Well, I guess the other thing is we really want to read our initialization file. Verify that we can actually read the code where we're going to store that. And if we can actually do that today, then I will call it a smashing success. All right. So it seems like the cartridge still works. Which is good. We don't actually know that our program is working, but we at least didn't break. You know, we're not spitting data out on the CPU data bus when we're not supposed to be, which would crash the game. So this is the INL Retro code base here. I just want to let's use the Action 53 test ROM. Okay. What? Program manufacturing ID is BF. That this is an AMD flash on there. I don't know that that actually works on this mapper. Anyway, so let's just do So let's read it from 6001. So we're doing 3 reads. I'm not 100% sure these are going to work, because I think this firmware might be too fast. Looks like maybe we got some right. If we just do a second read, then we kind of cheat the being too slow. So that's actually our initialization data. 6000 is here's the last byte of memory, FF. And here we set these. So that's a good sign. How many did we initialize? For 7. So if we read from 8, we should get 0. It's not very confirming to have the address be the same as the data. We should be doing something else, but it looks right. So let's just power cycle it by unplugging it and plugging it back in. Yeah. Let's try to write to it. So this is basically telling us that we should be able to PR our source code. What have you gathered? You picking up what we're putting down here? KOTD. Are you talking about a Super Nintendo cartridge again, or are you talking about NES again? Or the idea we're talking about before with the Super Nintendo? So this is so let's do that. Doesn't look like we're writing, but I'm not 100% sure it's a problem with the board. It might be a problem with the INL retro speed. Theory have on the cart, you can theory have that mapped into the runner space. Yeah, but the APU isn't necessarily a problem because they were mapped to the die on the NES, but the Super Nintendo doesn't have. So this is the NES memory map. I'm assuming that you're still talking about the idea of trying to play NES games on a Super Nintendo cartridge in a Super Nintendo itself. So the I/O registers here include the APU and the PPU and all that stuff, but I don't think the Super Nintendo and the first bank of the Super Nintendo, I don't think it maps anything here. Well, that's might actually have stuff. A clone double console. Well, if you were making a console, if you had design control of the console itself, then it'd be pretty easy to do. So this is bank 0 through 3F. Addresses here, it is actually there. You got this conflicting here. This might be in the same spot. This area is unused, so you should be able to put something there, but did I get rid of? This actually doesn't cause problems. This is where you put your program. Yeah. If you have complete design control over the only problem is well, you might be able to make it work because right, so the PPU is registers 2000 through 2007. There's only 8 registers, but then this whole space is just they're mirrors of the 2000 because it doesn't completely decode all of this on the main board. So you could put PPU registers here in this unused space. Now the original NES, if you wrote to this other space, right, these mirrors for the from 2008 to 3FFF, they actually end up back down here at your 2000. Assuming that no game writes up there, assuming they end up down there, then it would work. And here they're just putting the main board WRAM in 0 page through to, so there's already RAM. Both NES and Super Nintendo have. I mean, they could. I can't know if any games did. I mean, it's possible they could have. Whether or not it's not normal, but nothing's stopping them from doing it. Yeah. Hey, Betsy Adams, how you doing, man? Yep. So you're oh, we were talking about you earlier, Batsley. Somebody was Wow, Jinxie was wondering about your dual port RAM board. If you ever had extras of those. I don't know what he was wanting to do, but he was curious if he was wanting to get one. I don't know if he was able to install it himself or what, but right. Yeah, legal op codes. There's that whole situation. That's a conceivable problem. But I would think that most games, there's not many original games that use legal opcodes. I think some of them probably did somewhere, but most of the legal opcodes are homebrew. But I don't know how all of those. I mean, the other thing is like, do some games enable binary or decimal mode, but it's not even available? So like, there could be some incompatibilities created there. Yeah. One of our viewers was asking about one, but I don't know what his abilities were. Yeah. Desoldering memories from this guy. So you've got my green screen. I'll put it down. Oh, that totally messed me up. That's sweet. There, I'm back again. But you've got to desolder the RAM chip in that dual layer thick board. It's at least not a DIP 40 like the PPU and CPU. And if you destroyed the RAM, it's not as bad. I mean, you could just clip all the pins and throw the RAM in the trash. So then you're only desoldering one pin at a time, which isn't as terrible. I guess the other thing is depending upon the board setup, you only really need to disable this RAM. But anyway. Yeah. Yeah. I've just got one of those bulbs too. But I've used back in my Navy days, we had I forget what the brand was, but it wasn't Hakko. Yeah. I overall, I think it would be possible. I mean, the other thing is like, you could always like insert extra like logic on your main board, put a register somewhere that toggles between the two memory mappings. Yeah. So it would be interesting to have a console with both of them, Super Nintendo and Nintendo. I mean, yeah. What you would somehow you got to tell the console which. I guess it could check, but anyway, you got the whole issue of having to replicate the PPU and everything. Yeah, how much was that stuff? It's cheap now. the cheapest way to get dual port memory is like with an FPGA. Just do memory. So surface mount. No, I haven't seen those. I don't think. Is the R? Well, the visual. You're saying Rico 2A03. Those are. Yeah, $10. $8. Yeah. So this is, and this is only. Oh wait, this is 9. Okay, here we go. 2K by 8, 30 nanosecond. Hey Watson, how we doing? Yeah, so $10 for a 2K by 8. Our FPGA here, we've got 9K. Well, 8K by 9-bit. That 9th bit costs you some logic to implement. If we only have 8-bit data bus, yeah. And this FPGA is cheap, like $2 to $3 in individual quantities. Yeah, this is the GW1N-1, the smallest. I'm using the smallest because that's my business. GW1N-1. So it's got 1152 LUTs, 800 some flip-flops, 72K bit of block RAM, and that can be dual ported, true dual port. There's 4 separate block RAMs, but in total there's 72. And then you've got 96K bit of user flash, which is 12K byte. Yeah, it's sweet. We got a PLL, so you can multiply I connected the NES clock M2 Phi2 1.79 megahertz up to the PLL input. The datasheet says that it's supposed to, that the PLL input needs to be 3 megahertz or faster. I don't know. I'm not a PLL expert, why that would matter so much, but I tested it and input the 1.8 megahertz and it multiplied it just fine. I have a couple different ones. So I use the Kaio Razor for my CRT. When this is, I don't know what's on this board. I think this might be a broken radius 0. We'll put our Action 53 back in there. So this is, I found that this the Kaio Razor does a semi-decent job of capturing my CRT. I did get one of the super cheap on AliExpress, or not AliExpress, but yeah, I think it's Pi. I didn't go with the Elgato. It was cheap and I decided to try it. And it actually is okay. I've had good luck with it overall. So I use this guy when I'm capturing HDMI. From like my NT Mini and stuff like that, but this guy is what I use for the CRT, and then the webcam is just, what is it? The cheapo Logitech C615. So I've got one facing down here, and then the one from my face here. They get the job done. That's pretty. There's like one step up that is really popular, but the thing I was worried about, or most concerned about when buying multiple cheap webcams, is I don't think I paid $70. eBay $50. Anyway, my concern was like, am I going to have multiples of these? Is my computer going to be able to handle multiple at the same time and not getting confused? There like is a little bit of an issue trying to like fine tune the focus and stuff, but yeah. So anyway, yeah, we seem to have mostly successful. Well, we got some stuff working here. Our goal of today's stream is to make progress towards making the block RAM inside the FPGA act as a boot ROM to select which memory is the NES boots from. So I think I'm just going to call this our recap here, although I did want to try. So far we're booting from the 5-volt flash, which is I have an Action 53 build, but it's a smaller one, so it's only half the games or whatever. And all we really did was add block RAM to this mapper in the program location. We stored these values. So these were because it's block RAM, we're able to have Gowin provide startup values, so we can actually put code in there and it'll be present and effectively use it as ROM at boot. I just dumped in these starting values 1 through 8 for the first 8 bytes, and the last byte of RAM I put FF. And so with INL Retro, we read those values back out. It seems to be working. We tried to write to them and it didn't work. I am a little bit. I think part of that might be just because I think it might be a speed issue. I think the INL Retro might be too fast because when I was testing with this stuff before, that's my best guess. But we could have a write enable problem because both reads are the same. It doesn't. Here's where we do our write. Yeah. So we're unable to write for one reason or another, but we're able to read to it. So we're making. I mean, ultimately, to use it as a boot ROM, we don't need to be able to write to it. But of course, I want to fix that anyway. So right now, we have this set up where the 5-volt flash, yeah, I tried to get their Game Boy and failed. Their previous launches weren't hard to get at release, because I got their Super Nintendo and their Genesis at launch, and I think if you ordered that first week or whatever, they were pretty, but I think they might have actually just been open pre-orders. I don't know. Getting one after that time, you gotta like wait till they do them. But the Game Boy, I was leisurely logging on after they opened up for pre-order. I just wanted to be towards the front of the list, and then by the time I got to checkout, it was gone. So whatever. It's not really available till next year anyway, so I'm a little bit hesitant. But so let's what I wanted, the part of my concern here is it's easier to execute from the 5-volt program, and we're able to read from the block RAM, okay, and the game still executes. But if the block RAM and the 3-volt program are both behind the level shifter, so there's a few more things I have to get right to be able to do those things from the 3-volt ROM. So let's swap those out. So we're disabling the 5-volt program, enabling the 3-volt, and this was the logic when there wasn't block RAM, but now that there is block RAM, we need to add this in. So if ROM select is low and we're reading from the program, we need to read from the cartridge, or if we're reading from the block RAM, we need to set the directionality out of the cart. So let's see if this works. If it doesn't, then I don't think I'm gonna worry too much about it. I'm starting to get hungry and ready to call it here. Okay. Let's try the INL retro here. Oh, I think I need to power cycle it, or I just broke it all. Yep. I wonder if it boots. Oh, wait a second. Never mind. My kick was disabled. There it is. The lockout chip has to tell the FPGA to reconfigure, otherwise it tries to configure itself externally. So that's working still. Good. Okay. Now we should have the full volume 3. Oh, we do not. Unless you know what? I think this isn't actually I think I have the small ROM flashed. Gotta go. To my other folder. See if we can flash it. Where is it? Released. That one. Okay. We got the manufacturing and product ID for the 3-volt ROMs, so it looks like we're good. But if I have the same ROM flashed on both things, I don't have a great indication that we were playing from one or the other, but I'm going to say we probably were. Confident enough just because of this. But yeah. So let's just go ahead and do a recap here for our NESnet stream 15, I think, today. Getting the cobwebs out of our Wi-Fi project. We've got a new board layout that has the new Gowin FPGA, and it already has the footprint for us to have the ESP plugged directly in there. This is the layout here. So the final release of this hardware for my sneak release of the Wi-Fi stuff is going to have a 2 megabyte prog ROM. That's a 3-volt ROM behind the level shifter, and that's where the volume Action 53 volume 4 game image is going to be stored, and we're going to write protect that so that it can't be erased, at least not unless people start loading up their own configurations and stuff to the FPGA. So we're trying to protect that, and then we have a separate 5-volt program, which is going to be the development program. Normally, we're going to boot from this ROM, the 6502 is. But if we hold a special sequence on the controllers, then we want to boot from the development program. We have to somehow control that. My initial thought was to put a boot ROM of sorts inside the Action 53 build, so that just always boots with control of 6502. But I realized we could kind of sidestep that need, so I don't have to. I can completely separate myself from the game code and instead have a boot ROM inside the Gowin FPGA, because we've got block RAM available, which we can dictate the startup values. So we've basically got a third ROM available, ROM, however you want to think of it. And so we added that. We use our code our IP generator, made an 8KB single port block RAM, and we connected it up, and we had the ability to create a memory initialization file, and we just for dummy data put 0 through 8 or 1 through 8 in the first 7 bytes, 8 bytes, and then through FF at the end. And so for right now, I'm just adding the block RAM to the Action 53 mapper. Get it all, make sure the block RAM is working, and then we'll worry about booting from it. So we did this little test. Or I can. So with the INL Retro, yeah. So this is, we just put some reads in here from the block RAM and read back the values, and here are the initialization values that we put into the Gowin tool. So we figured out, yeah, I do. So that's kind of why I do these little streams at the end, so people can, the whole thing I'll put on there, but in the beginning there's links to this recap at the end. So anyway, we succeeded in getting that block RAM into the 6,000 to 8,000 normal program range, and we initialized the values. So now we could start writing 6502 assembly, just typing it in here into this memory initialization file. We can do it separately here. There's just a text file. Yeah, so we can, it's not the most convenient, but the text, at least with the text file, we can just write a little Lua script or something to convert whatever bootloader we write in CA65, generate a 6502 binary, an NES ROM, and then convert that to one of these memory initialization files, text, and then in the IP code generator, when we instantiate the block RAM, we can provide a file here. And so then when we click generate, it'll make a new one of these files, the Gowin single port, and here's actually what the initialization file looks like. It doesn't, where you got the memory split up into 4 different RAMs, block RAMs, so somehow these bits correspond to that. I don't know how exactly, but we don't really need to understand that. Anyway, this then gets brought in. Here's where we're invoking that generated code, and we got everything connected up into the cartridge address and data bus, and we had to do a 8-bit buffer because this just has 8 bits in, 8 bits out. It's got 2 separate data buses. We had to make a buffer because we only have one set. There's only 8 pins bidirectional data bus on the 6502. So we did all that, and we read back our data, and the cartridge still works. We just reflashed the 2 megabyte 3-volt. We've got our, so this is just volume 3 here. to get my hands on the volume 2 ROM, but I need to replace the level shifter with the terminated one, get rid of those glitches. But everything's working here for our first steps to that block RAM. So yeah. Does anybody have any questions? Otherwise, we will wrap this up. I don't know. Maybe there's somebody we can raid. But that's next week. We'll I don't know what. I suppose we'll have what we really need to do next is we need I guess so we could write like a really simple loop in the initialization file, jumping, try and do these streams on Fridays. If all goes well, I start them around 9 or 10 a.m. Central Time. Today I didn't get started until 1 in the afternoon. But yeah, once we get I'm not doing my Wednesday streams anymore, because all was not. I'm no longer working on all what other people are, so I might start the Wednesday streams up again when we're at the point where it's ready to make a game for this, and maybe Wednesday will be my game dev streams and Friday will be hardware stuff for the Wi-Fi cart. But we got the block RAM all ready to go, so probably next time we're going to be moving the block RAM into the reset vector location at boot. We're going to have to create some registers to control what memories are mapped where. But actually, maybe we can just write a tiny little boot ROM in the block RAM here. Execute from it and have it make some writes to the mapper, which then enable the 3-volt ROM or the 5-volt ROM. And if we have that, then we're pretty close to enough to where we can release Action 53 Volume 4. And then to be able to unlock all the Wi-Fi hardware and SD card and stuff, you have to update the firmware with the INL Retro later on. But anyway, yeah. So thanks for joining. We'll catch you next time.